Okay, so we have looked at or practiced a couple problems on r squared and s. And now what we're going to do is investigate how r squared s and our regression line is affected by influential points. Now, I mentioned earlier that we've already seen influential points before, but now that we have some more descriptors for our relationship, we're going to revisit that. So to do that, I'm going to play a video from the AP board that I think is a pretty good introduction to this idea. Once that video is over, it's pretty short, we will answer the questions that are on this page that you have in your notes. Sorry, I had this loaded, but it logged me out. I don't mean to be wasting your time.
Hello, Steph.
I like this guy. Oh.
For today, we start topic 2.9, analyzing departures from linearity. And this video is going to demonstrate how to find and categorize influential points. So what exactly will we learn today? We're going to learn what is a high leverage point in linear regression. We're going to learn what is an outlier when doing linear regression. And what effects do different types of influential points have on the least square regression line, the correlation, and r squared. Well, let's look at an example. So we talked about this context before. We're going to look at it one more time. These are different supermarket locations in the city of San Antonio, where I'm from. And my former student, Linda Saucedo, noticed that her local supermarket offered fewer organic fruits and vegetables than another location from the same company in a wealthier part of town. And so she wanted to see if there was a trend here. And so she collected data on the average income in different zip codes in the city, and then the number of organic items offered at grocery stores in those zip codes. And this led to a linear regression model where we saw a positive trend. And this was the exact parameters of our least squares regression line for this model, negative 14.7 being our y-intercept, 0.001 being our slope. And what you can do with the least square regression line, as we know from the properties of least squares regression lines, is you can take the mean of the x variables. So the mean of these incomes for zip codes was 69,198. You can take the mean of the y variable, in this case that was about 52 items per these grocery stores, and that point will lie on the least squares regression line. And some points we could look at here is what happens when we remove points that are close to this mean point, specifically close on the x direction, points where the average income in the zip code is close to that mean value for average income per zip code. So we're going to remove what we call these low leverage points. You'll see why they're called low leverage in a second. When we remove those points, as we just did right there, the original least square regression line is the dashed line you see right there. The new one is the solid line. You can see it didn't seem to change all that much. So when we remove all those points that on the x-axis are close to our mean point, the least square regression line doesn't change an incredible amount. Now let's talk about removing high leverage points. So high leverage points, by contrast, are points that on the x-axis are far away from the mean point. Here are three high leverage points. They're unusually high compared to the x value of the mean point. So when we remove those points, take a look at what happens to our least square regression line as well as to the formula. When that happens, we can see here the line shifts a lot. Again, the dashed line is the original line. The solid one is the new one. And we can see a pretty substantial shift. Specifically, look at the equation, our y-intercept shifted a lot, went from a value of about negative 14 to negative 28. That's huge. So when you remove high leverage points, the least squares regression line, in terms of the slope and or its y-intercept, can be meaningfully changed. So that's how we define high leverage points. Those are points with unusually large or unusually small x values, i.e. far away from x bar, the mean of our x values in our data set. And if we remove them, they usually will have a larger effect on the slope, the y-intercept, or both of our least square regression line. So what about this point right here? Here's a very simple example, just here 6 data points. And we can see here's our least square regression line for these data points. And this point in green towards the bottom, what kind of point is that? Well, it's close to the mean of our x variables, So it's not necessarily a high leverage point because it's very close to that mean point. But it does still appear unusual. So how can we still categorize it? Well, let's look at the residuals from this least squares regression line. We can see the residuals all look to be similar in magnitude except for that green point. This has an unusually high magnitude residual. And we call this, when you see that, an outlier. When it's unusually high magnitude for its residual. And this will have a big effect on the strength of this relationship. To see what I mean, here is the least squares regression line with that point included and without that point included. You can see here the correlation value is much higher when that point is not included. And in addition, the coefficient of determination value, the R squared value, is also much higher. So you can see there's a big effect on strength from removing that point. So these are all types of influential points, to sum everything up. Influential points are points that, if removed, change the slope, the y-intercept, and or the correlation substantially in our model. So there are 3 types of influential points. There are outliers, which tend to change the correlation. There are high leverage points, which tend to change the slope and or y-intercept value. And there are points that are both, and those are also considered influential points. So here's an influential point that is high leverage in the first model you see up here. And if removed, we would think that this would change the slope and or y-intercept substantially. Here's an influential point at the bottom model that's an outlier. It's not a high leverage point. And if removed, we believe it would probably change the correlation substantially. And here's another kind of influential point where it's both a high leverage point and an outlier, has an unusual x value and an unusually high magnitude residual. If removed, we believe it would probably change the slope and the y-intercept substantially, as well as the correlation. So what should we take away from this lesson? High leverage points have unusually high or low x values. That's how we define them. And outliers have unusually high magnitude residuals. They don't follow the modeled trend as closely as most data points. So points are considered influential if, when removed, they affect the slope, the y-intercept, and or the correlation. And as always, statisticians, when analyzing data, be critical, be cautious, be compassionate, and of course, avoid BS, bad statistics. Thank you.
Okay, so let's talk about it in terms of what you guys see on our note sheet. Let's highlight some of the things that he mentioned in his video. So one of the first things is influential points have a substantial or noticeable change on some of your values and your regression line. So they have noticeable, substantial, significant. I think in your can you do, it says sharp or like sharply affects your regression line. So any kind of word that describes a noticeable change in your regression line. Now there were 2 different types. It is, I think, helpful to know that there are 2 different types, but I do not want you worrying about or suffering over trying to figure out if it's high leverage or an outlier. But if it changes your slope or y-intercept, it is called a high leverage point. If it changes your correlation, so R squared. Correlation would be R and R squared. And their change would be similar. So if R increases, then R squared also increases. what has the biggest effect on correlation are what we would consider outliers. And the examples below, you have seen them before. We're just going to revisit them in terms of the new S and R squared that we discussed in the first part of this lesson. So this is our original data, no unusual points, and the information for the line, correlation, and S are given in this little box. Now, normally we wouldn't extend this all the way out to 35 because our X values are all less than 10, but they're trying to show you what this relationship would look like if you went past 10. So our first case is a high leverage. Now let's remind ourselves that this is unusually high or low X values. So high leverage is unusually high or low X values. I always forget about the low part. I'm used to recognizing that if we have a point that's way out here in the X, of course that's going to affect our line. But there will be some data sets where you will have a point to the left that is unusually low. That is also going to cause some issues for your line. So we have previously talked about how if we put this high leverage point up here in the pattern and it has a large X, this is going to strengthen your R. Your R goes from 0.41 to 0.94. Your R squared also increases. So the one other thing to talk about then is S, our prediction error. Well, remember, our prediction error tells us how far we are off from the actual value. It's talking about the size of your residuals. Remember, residuals are how far your points are from the line. So we're talking about, if I zoom way in, the size of these distances. Okay, well, now if I include this new point, he is very, very close to the line, which means that his residual is very small. Because it's very small, that means S will decrease. This point is very close to the prediction, so that will decrease your residual, your average residual. The closer a point is to the line, the smaller the residual, the farther away, the larger the residual is. So this decreases S, which we want because it's so close to the line. Are you guys okay with that? Okay, this example isn't as helpful as I think that it would be if you put the point here instead. So he's still an unusually large X value, but now he is farther away from the line. In fact, it'd be even more helpful if I put him a little farther away than that. So now let's talk about what would happen if this were our actual point. And let's talk about what would happen in terms of A, B, and S. So if you have a point here, what that's going to do to your line is flatten it out a little bit. Now, I'm exaggerating the effect that this would really have, but the idea is the same. It's going to flatten your line out. I think maybe I'll highlight that. So, in terms of y-intercept, it increased. Notice that because your line flattened, your y-intercept increased. So I'm just going to put an arrow pointing up. Your slope will decrease. And when you think about your slope increasing or decreasing, I want you to think about the steepness of your line. If the steepness increases, that means the slope increases. And if the steepness decreases, that means slope also decreases. So think about slope as the steepness. Do not think about it as the actual mathematical value. Slope, think about an increase or decrease in terms of steepness. Now let me give you an example of this. Negative 5 3/4, positive 1. Which line is more steep? Negative 5 3/4. But which slope is smaller? Smaller in quotation marks. Negative 5 3/4. So if you think about these mathematically, this is a smaller slope than this. But if you think about it in terms of the actual idea of slope, this slope is bigger than this slope because this one is steeper. So think about slope in terms of steepness. Are you guys okay with that? Okay, what will happen to your S value? So notice how far he is from the original line. It's going to increase your S. Your residuals are going to get bigger. Not only because of where this point is, but also because of how the new points down here will relate to the new line. The next one is also a high leverage point. The next one is also high leverage because he's unusually large X again. And I think it's easy to see how this has affected your relationship. Your correlation has gone from positive to negative, and it's even weaker than before because this line is not a good fit. Without that line, you would have a positive relationship. Y-intercept is much bigger. Slope is way less steep and now negative. And S is about the same. It's a little bit bigger, but I think that maybe I would say about the same. Slightly bigger, which is, for all intents and purposes, probably categorized as about the same. Some people are bothered by the fact that S doesn't change by all that much, but if anything gets a little bit bigger. And so there's an explanation if that's something that you thought of. So even though the new point has a relatively small residual, the standard deviations got a bit bigger because the line doesn't fit these remaining points as well. So our points became, on average, a little farther away from the prediction line. And then lastly, you have the case of the outlier. And what makes this guy an outlier is two things. Number one, his residual is very large. So large residual. But the other thing to notice is he does not have an unusually large X value. He is in the same interval that the rest of the X values are in. Does that make sense, what's happening there? So here's what happens to the line, and I think that this is very interesting. It doesn't change the slope of your line. It moves your line up. So the line has the same slope, but that X value pulls it, or sorry, that Y value pulls the line up toward it. So slope stays the same because this has a reasonable x value. It is in the same area that the other x values are. The only thing that's different is the y value. So it takes that line and pulls it up. Keeps the slope, just changes where it's at. The reason why that is, I keep saying it and I'm hoping that it's sinking in, is because this x value is in the same interval as the other ones. So what effect will an outlier that has a large residual have? Well, it changes R substantially. R is essentially 0 now for this model. It goes from being weak, 41, to being like 11. That's huge, a huge difference. And then S will always increase. If you add in an outlier, S will increase because an outlier by definition is a point that has a very large residual. Are you hanging in? Okay, so before we end this lesson and do the lesson questions, I want to investigate what happens when you have influential points by adding some of them to a graph and seeing exactly how it changes slope, y-intercept, and all the important values. So I'm going to bring around your Can You Do while you guys go to this website. Go to Statlet.com. That stands for Stat Application. You're going to Statlet.com. Then in your Can You Do, you're going to the second page. This is your Can You Do's for the rest of the unit. Don't be scared.
Yeah, I saw it in that first, I was like, oh.
No, take it back. Okay, second page, Statlet.com. We'll go into the second page. And we are going to investigate what happens to scatter plots descriptive values when we add influential points. So I'm going to change my screen now to Statlet. And we are choosing 2 quantitative variables. This does not give us names for our X and Y, so we're going to skip the name, but we're going to type into our explanatory our X values. So I'll cover up the Y's with my finger. We're typing in 2 space 2 space 4 space 4 space 5. Then in your Y values, you're typing in 3 space 5 space 4 space 7 space 6. Where are all my spaces, family? You want to begin analysis. And it gives you your scatter plot. So now I'll zoom out a little bit. Okay, calculate correlation. This has a correlation of 0.589. Is anybody getting 1? Okay, then below that it says calculate least squares regression line. And it gives you your regression line, your residual plot, and then down in this little box, it gives you your equation, your S and R squared. So we fill that in here now on our paper. The black dots and the line on this graph are for the 5 points, these 5 original points. And the equation for these 5 points is y hat equals, what is it? I already forget it. Oh, let's round to the hundredths. So 2.64 plus 0.69x with an R of 0.589. Are you okay? Yes or no? Yes or no? Okay. So then what you see is all of these additional points added. All of the points in these squares are new points that we're putting on to see what happens. We're adding them because it's easier. It's easier to add these points than to take them off. So let's talk about it in terms of just where it's at on the line. Do you guys think this is going to affect the relationship, this point? No, because he's right in with the other points. Is it going to affect your line of regression? Probably not, because he's, once again, by the other points and next to the prediction line. Will it affect S? Yeah, I think that S will probably go down a little bit, because notice he is closer than 4 of the points. So S, I think, will go down, but everything else I personally think will stay the same. That's what you're seeing down here in the table. So the gray line, sorry, distance learners, I forgot to change my screen. The gray line, or the gray row, is our original data. So it is the information that we just found out and filled in up top. This is what happens if you add point A. Your equation changes to this, and notice I've gone through and indicated what has happened and what the values changed to. So everything but S, like we talked about, stayed the same or about the same. You guys okay with that? Are you sure? Okay, now let's add in, let's do F. So let's skip all the way to F. So what we're looking at, and I'm going to go to Desmos so that you can see this, because it's not, your regression that we're using is not going to let you do this. So we're looking at what happens if I now add in this new point to my regression line. Everybody understands that that's what we're doing, yeah? Because your Staplet is not going to let you see it like this. Your line's about to change. So we're going to see what happens when we add that. Well, let's make some predictions. So in our table, let's just quickly make some predictions about what we think will happen. So we are going to skip the line because we're not going to predict the line, but let's see. What do we think is going to happen to S? Increase, decrease, or stay the same? So I'm hearing, I'm not sure if that was an increase or a decrease. Decrease? Why? Because it's very close to the prediction line. Okay, strength of our relationship. Increase, decrease, stay the same. Increase. These are our predictions. Slope. Do you think the slope of your line is going to change? Not very much, so that's probably going to be about the same. R squared is easy. If we think R is going to increase, that means R squared is probably going to also increase. Okay, well now let's actually see what happens. We go to our Staplet. We're going to fill in 10. So we scroll back up, do space 10. Now when you click down in the Y, it's going to say, are you sure you want to change your data? You say yes. Space 9. and you begin your analysis again. So now your point's there. We calculate our correlation, and it did increase. Our correlation is now 8, 4, 7. And I'm filling that in my table. We calculate our least squares regression line, and we see if we were right. So our new line is y hat equals 2.87 plus 0.62x. Now let's check in on what we predicted. Oh, I forgot to grab S. S is 1282. So we were right, S decreased. S went from 1475 in the gray row to 1282. Correlation did increase. Slope went to 0.62. Is that what you guys got? Yes? So slope decreased a little bit. R squared did increase. I didn't write it down, so I'll just square 847. So 0.717. Is that what the table gives us? What does it give you? Did I do this wrong? 718. Got it. Do you guys feel okay about that? Okay, so I want to spend 5 minutes on this, but make sure that you hear me on this. Are you listening? You are going to get the most use out of this if you predict first and then check the line. Do you see what I'm saying? Okay, give it a try for 5 minutes, and then we will finish up this lesson. If you are a distance learner, you can do this part as your can you do, and you move on to your lesson questions now. Okay, love you.